Hello everyone, I'm Shigang. Today I will discuss how to use partial collective operation to deal with unbalanced training workloads in deep learning. We propose a new algorithm called eager-SGD, which is essentially an asynchronous, decentralized SGD algorithm. It uses one training step to globally propagate the local updates. Before getting into the details, let me first briefly recap what is deep learning and how to scale up the training process of deep learning. Here we define a simple neural network model and an overall objective function f. In the objective function, W denotes the model parameters, and capital F is the loss function. C is a data point sampled from a distribution D. So the training process is essentially to optimize parameter W to minimize the overall objective function f using some optimization method such as SGD. However, as the training dataset and model size increase, we would like to use more computational resource to speed up the training process. So how to scale up the training process of deep learning? We can use model parallelism, in which the neural network model is partitioned into pieces, and each process is responsible for one piece of the model. Before calculating the intermediate result of the current layer, each process has to gather the intermediate result of the previous layer from all the other processes. We can also use pipeline parallelism, in which the neural network is partitioned in a layer-wise way, and each process is responsible for one or several layers, which forms a single pipeline stage. Each process has to transfer its output data to the next pipeline stage, namely the next process, to progress the whole pipeline. We can also use data parallelism, in which each process maintains a copy of the whole model, and each process will randomly sample different data batches from the training dataset, and it will calculate different gradient values. After that, it will do a global synchronization to synchronize the gradient values using a standard allreduce operation. For data parallelism, it's simple to implement and usually efficient. So data parallelism is the most popular method to scale up the training process of deep learning. However, what's the problem of data parallelism when we have unbalanced training workloads? For example, we may have load imbalance from the application level. In recurrent neural network, RNN, LSTM, GRU, the input size and output size may be changing during training, which means the workload may be changing during training. Another example is heterogeneous environments in deep reinforcement learning. In deep reinforcement learning, each worker has to generate the training dataset online by interacting with the environments. However, if the environments are heterogeneous, each worker may use different amount of runtime to generate the same amount of training dataset. We may also have load imbalance from the training system itself. For example, on a multi-tenant cloud machine, it may have performance variability because of resource sharing. Even on high-performance cluster, it may also have some performance variability because of system or network noise. All these imbalanced training workloads bring us a challenge, namely, the regulars among all the workers dominate the performance of the whole training system. Next, let me show you some detailed example for the unbalanced training workloads. Here is a many-to-one RNN, many input to one output recurrent neural network for a video classification task. Here I unfold this recurrent neural network according to the time steps. To calculate the hidden state value ht, it will use the current input value xt and the previous hidden state value ht-1, and at last it will calculate the hidden state value h capital T. Here capital T is the number of time steps. After that, it will be connected by fully connected layers, and finally, it outputs the probability distribution over all the video classes. In the backward path, it will calculate the gradients in each time step, and then do a summation over all the gradients of all the time steps to get the final gradient value. Here we can see the workload of this recurrent neural network is proportional to the time step t. Here, capital T is equal to the number of frames of the input video. These figures show the workload statistics for video classification task to train LSTM model on USF11 dataset. On the left figure, it shows the video length distribution for the training dataset. We can see the video length is distributed in a wide range, and correspondingly, on the right figure, it shows the runtime distributions for the mini batches to train LSTM model. We can see the runtime for the mini batches is also distributed in a wide range. So all these statistical results show that this video classification task has severe load imbalance. So this figure shows the statistics to train ResNet 15 on ImageNet using a Google Cloud machine. From the application perspective, to train ResNet 15 on ImageNet, it doesn't have load imbalance. However, when we train it on cloud machine, because of resource sharing, it do have some performance variability, and we can see the runtime of the mini batches is distributed in a narrow range. So compared with the load imbalance from the application level, for example, the LSTM model on USF11, the load imbalance on cloud machine is relatively light. Now we have the problem for load imbalance, how to solve it. Actually, some of the existing work bring us some idea. To reduce the communication overhead, people use gossip-based SGD, in which each process only communicates with its neighbors in a certain topology. To reduce the communication volume, people use gradient specification techniques, in which only the gradients with significant values will be transferred. People also use gradient quantization techniques to reduce the communication volume, in which it uses less number of bits to represent the gradient value. People also use hidden unit dropout techniques to increase the generalization performance, in which about half of the hidden units are randomly selected to be omitted. So all this existing work actually shows that the deep learning training process is quite robust. To solve the load imbalance problem, we propose eager-SGD, which also utilizes the robustness of the training process. On the left figure, it shows the standard synchronous SGD, in which after each training step, it will call a standard synchronous allreduce operation to synchronize the gradient value. On the contrary, on the right figure, for eager-SGD, after each training step, it will call a partial allreduce operation to average the gradient value. By partial, it means only a part of the processes will contribute the latest gradient value. The other process may contribute stale gradients. By stale, it means the gradients are contributed by some slower process, which lags behind of the faster process in terms of the training step. So here we can see eager-SGD actually exploits the robustness of the training process by allowing allreduce on stale gradients. This table shows the difference between eager-SGD and gossip-based SGDs. Different from gossip-based SGD, eager-SGD also require all the process to participate the communication in each training step. However, the communication is implemented in a asynchronous way. We will discuss this later. And for eager-SGD, it uses only one training step to globally propagate the local updates. Next, how to implement partial allreduce operation. For partial allreduce, it has two phases, the activation phase and the real allreduce operation phase. The activation phase is used to trigger the allreduce operation phase asynchronously. Here in this example, we have 4 processes, and we suppose P3 is the fastest process. We call it as initiator. P3 will send activation message to P2 and P1. After P2 receives the activation message, it will continue to send activation message to P0. So in this way, the activation message is broadcast from initiator P3 to all the other processes following a binomial tree topology. After the processes are activated, it will trigger the real allreduce operation. So here for both activation phase and the allreduce operation phase, all the operators are progressed by an auxiliary thread in the background. So the execution is asynchronous. In some cases, we may also have multiple initiators. So this means more than one process may arrive at the collective operation at the same time. So in this case, in the implementation, we guarantee the same operator is only executed once, even if we have multiple initiators. For partial allreduce, it has 2 variants, solo allreduce and majority allreduce. For solo, the fastest process is the initiator, and it will trigger all the other processes. It's a wait-free operation, and at least one process, namely the initiator, will actively participate in the communication. On the contrary, for majority allreduce, we randomly specify a process to be the initiator, and the other process will wait for this randomly specified initiator. And statistically, about half of the process will actively participate in the communication. So for these 2 variants, we select to use a better one in different cases. We will discuss this further in evaluation. After having the partial allreduce operation, we implement eager-SGD based on TensorFlow. We define a customized distributed optimizer based on TensorFlow and implement a customized operator in which we will call the partial allreduce operation. And we integrate the customized operator into TensorFlow computational graph, and the operator will be executed after the local gradient calculation, but before applying the gradients. We also define a control dependency to make sure the allreduce operation are called in the same order on different processes. Because we integrate the operator into TensorFlow computational graph, actually eager-SGD also utilizes the execution engine of TensorFlow to exploit the parallelism in the computational graph, which means the communication and the computation overlap is automatically enabled in eager-SGD. Here is an example for execution of eager-SGD algorithm. So here we suppose we have 2 processes, and P1 is the faster process, which will be the initiator. But next, P1 finishes the calculation of the gradients of step T, and then it triggers the partial allreduce operation. However, at this time, P0 haven't finished the calculation of the gradients for step T, so in this case, P0 only contributes a null gradient. But after that, P0 finish the gradient calculation in step T. However, it discovers that the partial reduce operation is already done. So in this case, P0 will copy the stale gradients into its send buffer. And in step t plus 1, P0 somehow catches up P1. So in this case, the stale gradients are combined with the latest gradients and commit together to the partial reduced operation. We also theoretically prove the convergence of the eager-SGD algorithm. Here we only show the conclusion of the proof. For the detailed proof, please refer to the paper. So for learning rate value alpha, which is bounded by this formula, eager-SGD converges after capital T iterations. In the formula, tau is the staleness bound, which is the number of steps that the slowest process lags behind of the fastest process. P is the total number of processes, and Q is the number of processes which contribute the latest gradients. So here, P minus Q is the number of processes which contribute stale gradients. From this formula, we can also get the relationship between the training iteration T and the staleness bound tau and the number of stale gradients P minus Q. We can see if we use too many stale gradients in eager-SGD, the algorithm still converge, but it will use more number of iterations to converge. To evaluate the performance of eager-SGD, we use Piston supercomputer. On Piston, each compute node contains one Intel Xeon CPU and one NVIDIA P100 GPU. We compare the performance of eager-SGD with the standard allreduce-based synchronous SGD, including Workload and DP500, and the asynchronous centralized SGD, which is implemented in Tensorflow parameter server, and the gossip SGDs. We use 4 different neural networks to do the evaluation, including Hyperplane regression, ResNet, and LSTM model on UCF11. For Hyperplane regression and ResNet, we use simulated load imbalance according to the traces on cloud machine. For LSTM model on UCF11, it has inherent load imbalance, as discussed in previous slides. This figure shows the performance for hyperplane regression. The x-axis is the training time. The y-axis is the validation loss. We train equal number of epochs for all the algorithms. And here, the black, blue, and green curves are for eager-SGD using solo reduce operation. So here we can see for eager-SGD using solo reduce operation, it achieves significant speed up over the standard synchronous SGD. For the loss value, eager-SGD is equivalent with the standard synchronous SGD DP500. This figure shows the performance to train ResNet 15 on ImageNet. The x-axis is the training time. The y-axis is the top one test accuracy. We train for equal number of epochs for all the algorithms. So here, the blue and green curves are for eager-SGD using solo reduce operation. We can see for eager-SGD using solo reduce operation, it achieves a certain amount of speed up over the standard synchronous SGD, including Workload and DP500. For the top one test accuracy, eager-SGD is almost equivalent with the standard synchronous SGD. On the right figure, it compares the throughput between eager-SGD and the asynchronous centralized SGD algorithm and the gossip-based SGD. You can see eager-SGD still achieves the highest training throughput among all the counterparts. So this result actually shows that if we have light load imbalance, for example, the load imbalance caused by the system, solo reduce is enough to achieve higher training throughput and also reasonable accuracy result. This figure shows the performance to train LSTM model on UCF11 dataset. The x-axis is the training time. The y-axis is the test accuracy, including both top 1 and top 5 test accuracy. So here we only focus on top 1 test accuracy. We train equal number of epochs for all the algorithm. And here the purple curve is eager-SGD using solo reduce operation. And the blue curve is eager-SGD using majority reduce operation. And the red curve is the standard synchronous SGD hoverboard. We can see for the training speed, eager-SGD using solo reduce operation achieves the highest training speed. However, for the top 1 test accuracy, eager-SGD using solo reduce is about 10% lower than the eager-SGD using majority reduce and hoverboard. On the contrary, for eager-SGD using majority reduce, it achieves about 1.3 speedup over hoverboard. And also for the top 1 test accuracy, eager-SGD using majority reduce is almost equivalent with hoverboard. The reason for eager-SGD using solo reduce has lower test accuracy than the others is because for eager-SGD using solo reduce, it may use too many stale gradients. So this result actually shows that if we have severe load imbalance, we should use eager-SGD with majority reduce. So all these results are consistent with our theoretical analysis. Finally, I conclude this work. So eager-SGD can deal with the unbalanced training workloads in deep learning using partial or reduce operations. For eager-SGD, it has 2 variants, solo and majority. For solo reduce, is suitable for light load imbalance. For example, the load imbalance caused by the training system. While for majority reduce, it is suitable for severe load imbalance. For the future work, we will verify the idea of eager-SGD on model averaging-based SGD algorithms. So this is all the content for my presentation. Any questions?